let's talk about what really makes your computer, and for that matter, the entire internet, feel so fast. And spoiler alert, it's not just about having the fastest processor. There's a clever, hidden system working behind the scenes, and today, we're going to pull back the curtain on this unsung hero of modern computing, caching. So here's the game plan. We're going to start by talking about feeding a hungry giant that lives inside your computer. Then we'll reveal the simple, elegant solution that keeps that giant happy. From there, we'll explore a whole hierarchy of speed, from your CPU all the way out to the web. And then we'll bring it all home and talk about what this means for you the next time you're looking to buy or build a PC. So, what's the big problem we're trying to solve here? Well, it all boils down to a fundamental issue. A massive speed mismatch between how fast your processor can think and how fast it can actually get the data it needs. I mean, seriously, think about it. We have these CPUs with billions of seconds per second. They're ridiculously powerful. So why do we still have loading screens? Why does anything lag at all? It's because the bottleneck, more often than not, isn't the brain. It's the trip to get the information. This quote from a Reddit user just absolutely nails it. No matter how fast the CPU can execute instructions, it will be bottlenecked by memory. And the analogy is perfect. Your CPU is this massive, powerful giant ready to devour work, but it's being fed with a tiny little spoon. That spoon is your main memory, your RAM. And the giant is almost always hungry, just waiting for that next spoonful of data. And if you put some numbers to it, the difference is just staggering. For a CPU to grab something from its fastest internal memory might take, say, 3 of its own cycles. But to go all the way out to your main RAM to get that same piece of data, we're talking around 250 cycles. In the world of a processor, that is an absolute eternity spent just sitting there, twiddling its thumbs, waiting for that spoon. All right, so we've got this massive feeding the giant problem. How do you solve it? Well, this is where our hero steps in. Engineers came up with a brilliantly simple and absolutely essential solution called the cache. So what is it really? Simply put, a cache is just a small amount of super fast and super expensive memory that sits right next to the CPU. Its only job is to hold copies of the data that the CPU has used recently, on the assumption that it's probably going to need it again very soon. It's all about keeping the important stuff close by. And this creates 2 possible outcomes. Every single time the CPU needs a piece of data, it checks the cache first. If the data is there, boom, that's called a cache hit. It's a win. The giant gets fed instantly. But if the data isn't there, that's a cache miss, and the CPU has to make that long, slow trip out to RAM. The whole goal of a well-designed system is to get as many hits as possible. But it's not quite as simple as having just one cache. The reality is much cooler. It's a whole system of layers, a hierarchy of speed, where each level is a smart trade-off between size, speed, and cost. Probably the best way to wrap your head around this is the desk analogy. Think of the data you're working with right this second. It's on a little piece of scratch paper right in front of you. That's your super fast L1 cache. The reference books you need are on your desk. That's your RAM. And everything else, that's in the library down the street, your hard drive. You're always going to check the scratch paper first, right? Of course, it's right there. And that's exactly what you see inside the CPU itself. There's the level 1, or L1 cache. It's incredibly fast, but absolutely tiny, measured in just kilobytes. Then you've got L2, which is a bit bigger and a bit slower. And finally, there's L3, the largest and slowest of the 3, which is often shared by all the CPU cores. Each one acts as a fallback for the one before it. Now, this whole layered idea doesn't stop with the processor. Not at all. The exact same principle is used for your computer's main storage, too. You can use a fast type of storage to speed up a slower one. We call this disk caching. A classic setup you might see is using a small, zippy solid-state drive, an SSD, to act as a cache for a giant but slower mechanical hard disk drive. You get the snappy response of an SSD for your most used files with the cheap, massive capacity of an HDD. In fact, your operating system is doing this all the time with something called virtual memory, using a chunk of your blazing fast RAM to cache data from your much slower main drive. Okay, so let's zoom out, way, way out. Because this exact same logic, keeping copies of data closer to where they're needed, is what makes the entire global internet feel responsive instead of painfully slow. It's true. Without caching, every single time you clicked on a website, your computer would have to send a request, potentially thousands of miles, to a single server and wait for it to come all the way back. The web would be practically unusable. So instead, here's what actually happens. When you want to go to a website, your browser first checks its own little stash, its local cache, for things like images and logos. If it's not there, the request goes to something called a Content Delivery Network, or CDN. This is a worldwide network of servers that stores copies of popular websites. Only if the CDN doesn't have it does your request have to make that long journey all the way to the original server. So you see, there are multiple layers here too. You have your browser cache, you have DNS cache, which is like a phone book for the internet, so your computer doesn't have to look up a site's address every single time, and then you have the massive CDNs that handle the heavy lifting for popular content. And it's important to know the difference between private and shared caches. Your browser cache is private. It's just for you. It can store info about you being logged in, for instance. A CDN, on the other hand, is a shared cache. It's storing the same public version of a web page for thousands of different people, which dramatically cuts down the work for the main server. Okay, so we've journeyed from the tiniest part of a CPU all the way out to the global internet. Let's bring it all back home. Why should you, as someone picking out computer parts, actually care about any of this? Because understanding caching lets you make way smarter hardware choices. When you're looking at CPUs, don't just get hypnotized by the clock speed. A chip with a larger L3 cache can make a huge, noticeable difference in gaming and heavy multitasking. When it comes to storage, that SSD caching and HDD trick is a fantastic budget-friendly way to get both speed and capacity. Knowing this stuff helps you read a spec sheet and understand what's actually going to make your computer feel fast. The impact of good caching is just incredible. A well-designed system can achieve a cache hit rate of 95%, sometimes even higher. Think about what that means. 19 out of every 20 times your processor needs something, it gets it almost instantly. That is the literal difference between a system that feels sluggish and one that feels instantaneous. So at the end of the day, the big takeaway is this. Caching isn't just some optional feature. It is the essential bridge that connects our absurdly fast processors to our much slower storage. Without it, all that amazing computing power would be completely wasted, forever waiting on that tiny spoon. And that leaves us with a pretty fascinating question to think about. This speed gap between our processors and our memory, it's not getting smaller, it's getting wider every year. So what comes next? What's the next clever layer of caching that engineers are going to have to invent to keep feeding the ever-hungrier giant?